Hi, I'm Dr. J, and this is my guide to cardinality. Cardinality is the size of sets. If you haven't seen any of my other videos before, you might want to check out this video here that will get you the introduction to sets and why we're talking about the size of those sets. The main reason we're talking about it today is because the size of the sets is related to random variables, in that random variables, when we discuss them, can take on a number of values, and the number of values that those random variables can take on determines mathematically how we have to treat those random variables. And so that's why we're introducing the idea here of cardinality, or the size of sets. As usual, down below there is a link to a printout of these slides. Alright, cardinality. Cardinality is how many elements are in the set. So just think of a few sets here. And here's the first set. It's a set we'll call A for the moment, and it has the elements, the integers 1 through 100. And this one's pretty easy. There's 100 elements in this set. But now it gets a little trickier. What if we think about all of the subsets of A? So if you start thinking about what a subset is, you can think, well, there's the empty set, and then there's the singleton set, so the set that has just the number 1, just the number 2, and there's 100 of those. So right away we're at 101. But now we can think about, alright, well, how many subsets of size 2 are there? That is, sets that have 2 elements in them. And there's a bunch of those, and we'll talk about how to get at that number in a future video. And then we can say, well, how many sets of size 3 there are, and 4, and 5, and 6, and all the way up to 100. And now all of a sudden we think, well, there's a lot of possible subsets. But even though there's a lot of possible subsets, there's still a finite number of them. That is, I can eventually determine exactly how many there are. Compare that to the set of natural numbers. The set of natural numbers, well, there's a lot of those as well, and in fact, the natural numbers just keep going and going and going and going, right? And so there's clearly an infinite number of those. All right, well, what about this? We have the open interval 0, 1 here. And now if we're thinking and we're trying to compare, say, to the natural numbers, well, we can construct numbers that are in this interval by taking 1 over those natural numbers, as long as the natural numbers are 2 and greater. So think about that as the positive integers 2 and greater. So if we take 1 over 2, or 1 over 3, or 1 over 4, those are all elements of this open interval 0, 1. And so there's at least as many numbers in this interval as there are natural numbers. But now we can go beyond that, and we can say there's even more numbers. So somehow this set here is really big. And now here's somehow an even bigger set, perhaps, right? Here's all of the real numbers, of which the interval 0, 1 is a subset. All right, so today's discussion is about the cardinality, or the size of these sets. So here's the cardinality of a set A. We denote that using what looks like absolute value symbols. And this actually relates to an absolute value, in that an absolute value tells you the size of the number that's inside it away from 0. And so this size is the same kind of notion when we're talking about a set. And the cardinality is just the number of elements in the set. And now we could go really into depth in this topic, but for our purposes, we don't really need to. What we're really interested in today is identifying when is a set finite, when is it countably infinite, and when is it uncountably infinite. And we'll talk about those notions in a second. Alright, so a finite set. A finite set is set is finite if its cardinality is less than the cardinality of the natural numbers. Another way to say this is that if you can start counting the elements in the set and eventually stop, because if you can stop, then there are less elements in that set than there are natural numbers, which there's infinite number of them. Alright, so here's some examples of sets that are finite. The number of cards in a standard deck of cards. Right? Without jokers, there's 52. With jokers, there's 54. But either way, there's a finite number of those cards. U.S. Social Security numbers. Social Security numbers are a 9-digit number using the digits 0 up to 9. And there's some digits there, or some combinations that you can't use in order to get Social Security numbers. But we have at least an upper limit on that number. And this is a large set. That is, the number of different Social Security numbers is large, but it's not infinite, right? It still ends at some point, and therefore it's finite. Here's another one that's even bigger, Right? Here we have 32-digit passwords where we're allowed to use letters, numbers, and symbols. And there are a lot of those kind of passwords. But yet the number of those passwords is finite. And here's another one. The number of grains of sand on a particular beach. Right? Now you think of yourself as going out and enumerating every single grain of sand. So you have grain 1 and 2 and 3 and 4. And it would take you a long time to enumerate all the grains of sand on any particular beach. But if you had enough time, you could do it. And therefore the number of grains of sand is itself finite. Alright, so that's finite. And we are going to be spending a lot more time on finite sets in the future. There'll be a whole series of videos. They will fall under the category of counting. And the counting ideas is determining how many elements are in a finite set. And we'll be able to answer these questions about social security numbers and passwords and so forth when we get to those videos. For now, all we care about is that there's a finite number of elements in these sets. Alright, so now in contrast, moving along, we have sets that are countably infinite, and sometimes we'll refer to that as countable. And the key here is that the cardinality of these sets is the cardinality of the natural numbers. And again, for our purposes, we've defined the natural numbers to include 0. And so the way that we're going to determine whether another set has countable cardinality is if we can put those two sets, that is the natural numbers and the new set, into a one-to-one correspondence with the elements in those two sets. So here's an example. The set of positive integers. Right? So this is now the same as our definition of natural numbers, but that does not include 0. And the question is, can we put each element into one-to-one correspondence between these two sets? And the answer is yes, we can. And it's pretty straightforward, actually. What we say is that the natural numbers, which start with 0, here will correspond that with 1, and then the 1 will correspond with 2. And so I've shown that here as a subscript in red. So the subscript in red is our definition of natural numbers, and then we have the positive integers in black. And our one-to-one correspondence basically just takes an element that's in the natural numbers and adds 1, and that will then correspond to the positive integers. And so we will say that these two sets, the positive integers and natural numbers, have the same cardinality. And that is, it's countably infinite. Now, if this is the first time you're seeing this, this seems pretty bizarre, right? Because the natural numbers, the way we've defined it, actually have at least one more element in it, right? Because it has the element 0, and the positive integers don't. But this is where things get weird when you talk about infinity, right? And so the key here is that the definition of countably infinite is that we can put the elements into one-to-one correspondence, and that's the key. So here's another example. The integers. So now we're including the negative integers and we're including 0. And so now we have to think about a way that we can put this into one-to-one correspondence with the natural numbers. That is some way of sort of, say, coming up with a function that turns one into the other and vice versa. So two functions, really. And so here's one way of doing it. All right, so we're going to start with the integer 0, and we're going to make that 0. And then we're going to take the integer 1 and correspond with that with the natural number 1. And now we have the integer negative 1, and we're going to correspond that with 2. And now we just keep repeating that process. And we alternate back and forth between positive and negative. And now what we've given is we've given a one-to-one correspondence where every whole number corresponds to one positive integer. And therefore, because we can do that, we will call that this set of integers to be countable or countably infinite. Here's another example that's maybe a little bit more realistic or interesting, and it gives an example of how in the future, when we get random variables, we're going to use this idea. So imagine that you're flipping a coin, and as you're flipping that coin, you're just recording the number of tails before you get your first heads. And the question is, what are the possibilities for the number of tails that you could see before you get one head? And so, of course, you could flip it on the first trial. So one element of this set is 0. But you could flip a tails and then a heads, in which case the element is a 1. Or 2 tails and then a heads, in which case it's 2. But if you think about this, you can flip a whole lot of times before you get a heads. It's possible. It's not probable, but it's possible. And so here, the possibilities for the number of tails that you flip before you get one heads, there's no limit to how large that could be. And so this actually corresponds to the natural numbers. And because it corresponds exactly to the natural numbers, this set is countable or countably infinite. Now let's talk about a set that's even larger. This set is called uncountably infinite or uncountable. And the definition here is that the cardinality is greater than the cardinality of the natural numbers. And the key here is going to be that we cannot put them into a one-to-one correspondence. That is, no matter what we try to do, there's always going to be extra elements of this new set than there are of the natural numbers. And now, I don't have time in this particular video to give you an example, or give you a proof of why this might be the case. But I'm just going to show you some sets that are in fact uncountable or uncountably infinite. In particular, we have the real numbers. Right? These are all the numbers that you're familiar with. They include things like pi and the square root of 2, in addition to all of those integers that we were talking about earlier. So the real numbers are an uncountable set. That is, they cannot be put into one-to-one correspondence with the natural numbers. There's always numbers left over in the real numbers in any way we try to do that. We can get smaller sets that are still uncountable. So here is the positive reals. And the positive reals, again, are uncountably infinite because there is no way to put them into one-to-one correspondence with the natural numbers. An even smaller set is the open interval 0, 1. We cannot put them into one-to-one correspondence. Again, there's always numbers left over in this interval when we try to do that. And so this is going to be the key piece in recognizing when a set is uncountably infinite. That is there any interval in that set? And if there is, then the set is going to be uncountably infinite. Here's a more practical example. Let's say reaction time. So perhaps you've been at a science museum and they have something where they show a light and you're supposed to press a button or something, or I don't know, a handspring or something like that. And it records how long it took you to respond. And now that length of time could be anything that's positive in this case. Right? It could take you a really long time, you could do it pretty quickly, but it's some positive amount of time. And so that actually corresponds to the positive reals, and therefore that set of possible reaction times is an uncountably infinite set. Alright, so in summary, we're interested today in talking about finite sets, where the cardinality is less than that of the whole numbers. We have countably infinite, where the cardinality is equal to the cardinality of the whole numbers, and we have uncountably infinite. That is, the cardinality is greater than the cardinality of the whole numbers. And the key to recognizing this last one is that if there's any interval, then it's uncountably infinite. And as I mentioned at the beginning, the main reason we wanted to discuss this is because mathematically, when we get to random variables, we're going to have to treat those random variables that have finite possible values or countably infinite possible values differently than we have to treat random variables that have uncountably infinite possible values. And later we're going to be talking about the first two as being discrete random variables and the last one as being continuous random variables. Now, we have finished up our section here on talking about mathematical sets. And if you recall, the whole purpose of talking about mathematical sets is because we're going to want to define probability, and probability is going to be a function of a set. And so next time, we're going to get to that definition of probability. For now, I hope you have a good one.